Okay, quick follow-up on the last video I did regarding this ANS simulator automatic version. The previous one I built was manual. You had to turn a little potentiometer to get the right voltage, and in the process now building an automatic one. Imagine that isn't there at the moment, this chip and these wires going across to those LEDs. This is what we had last time. We had our 3 buttons and this 4013 chip, which is a dual type D flip-flop, and we were using that as a latching device to latch these LEDs here. Okay, so latch the outputs of whatever we pressed on these two. So just to show you that, this is our clock cycle here, simulate the clock. So if I held down this first bit and cycled the clock, then it latches it in on the first LED. If I press down the second bit and cycled the clock, then the second LED illuminates. And if I did both together, then the 2 LEDs illuminate. Okay, so now what's this chip then? So I did mention it in the last video, but before we go into it on here, let's just have a quicker look at a diagram and see what we've done. Right, there we go. So basically this is a representation of what we got. It's not wired like this. It's just showing you in a sort of block diagram format. So this is the 4013 dual flip-flop. That's what we're using as a latching device. We've got the blue button that we had, which is representing our clock, with this which I've called button A and this which I've called button B. When I press this and cycle the clock, then it's wired out to LED A, and that will illuminate and stay latched. And similarly with B, if I press that, then that illuminates and stays latched. If I press them both, they both stay latched. Okay, and then what I said was we would feed this into a multiplexer. And I'm just going to bring up the data sheet of that before we go on to the next slide, because I've actually changed my mind on the version that we're going to use, and there's good reason for that. So let's have a look at that now. Okay, so this was the 4051 I was going to use, which I showed this little representation of the 4051, and whatever you put into these 3 inputs A, B, C, so a low being a 0 and a high being a 1, whatever you input there, this would route the corresponding channel to our common I/O, so it physically connects the two together. However, if you recall, I didn't need to use these 4 channels down here because I've only got 4 voltage references that I need to route through, and these were just going to be redundant. I would never have selected them. But actually, I've got a reason why I want to use this sort of dual channel multiplexer here, the 4052. Works exactly the same, it's just that it works in parallel. So there's only 2 address bits here, A and B. You haven't got the C like you have up here, and it actually operates in parallel with 2 multiplexers. It's a dual multiplexer. So if I select 0, 0 here, not only does it route this channel through to this common I/O, it also routes this channel through to this common I/O. So you can see they're called X and Y. So X0 will go to X common and Y0 will go to the Y common. If I put in 0, 1, then the X1 channel will go to the X common and the Y1 channel will go to the Y common, and so on. Okay, so it's you can see what it's doing. It's doing it in parallel. This behaves exactly the same as that. So this is switching through the X channels, and this one's switching through the Ys. Okay, so just go back to my block diagram then, and I'll show you how I've got that wired at the moment. Right, so that's what we had. Okay, so now if I add in the multiplexer, there we go. That's that same dual channel symbol. I've just rotated it, that's all. And what I'm going to do is this A output here and this B output here, not only am I going to keep them on the LED for now, because this is only really for demonstrating that it's working. As we build this up, we want to see what's going on. Okay, ultimately we won't have this on the final thing. But now if I parallel up my A to this A input on the multiplexer, and this B to the B input, not only is it lighting the LED, but it's also feeding into my binary input on this multiplexer here. And then if I take my, don't worry about the Y outputs at the moment, or the Y channels, we're not using that right now, but the X channels is what I'm going to utilise. If I just wire all of those, so look, X0 is going to this LED, X1 is going to this, X2 is going to this, and X3 is going to this. And I'm just, for the hell of it, I'm going to number them LED 1, 2, 3, 4. I know 1 is actually 0, but 0 doesn't sound good, does it? For first LED 0, 1 sounds better to me. So whenever I select 0, 0 here, this channel 0 is going to be linked to that common. If I select 0, 1 here on my AB, then it's going to be this channel, LED 2 here, is going to be linked to my X common. So if I just wire this X common up to 6 volts, then whatever address I've selected here and this is switched to, the corresponding LED will illuminate. So what I'd expect to happen is when I push the clock button and cycle it with nothing pressed here, I get 0, 0 here, that none of these will light. Channel 0 will be selected, and therefore this first LED here will illuminate. Okay, the A and B will be off, but that will illuminate. If I select 0, 1, in other words I press that and give it a clock cycle, then I've got 0, 1, so it will then switch this across to channel 1. 6 volts will route to channel 1, and that will illuminate LED 2. All right, so let's just have a look at the breadboard and see that working. Okay, so back to the breadboard. This is exactly what I had just now. Let's just clear that. Now, the X common on this chip, this is the multiplexer here. The X common that I said I'd pull up to or connect to 6 volts, that is this pin over here. All right, we're in the middle there, you can't really see it on the camera. All I'm going to do now is connect that up to my 6 volt supply, like that. There you go. And you can see straight away that LED number 1 has come on because we've got 0, 0 on my AB. Neither of these are lit, are they? Because I clock cycled it, cleared that. 0, 0 has selected channel 0 in here, which routes through to my 6 volts and illuminates LED 1. If I now put this to the AB to 0, 1, there we go. So this is now 0, 1, and my second LED has illuminated. If I do 1, 0, my 1, 0 here, my third LED has illuminated. If I do 1, 1 and cycle it, so I've got 1, 1 here, and my fourth LED is illuminated. Great, that's exactly what we wanted, but I didn't want to be pressing I don't want to be having to enter a binary. I wanted my 4 buttons, and when I press this one, I want it to select that. When I press that one, I want it to select that. It just needs to be one press, okay? And that was the priority encoder that I ordered, and it has arrived, and I will get that wired up and we will move on to testing that next. Okay, this was the multiplexer device, the CD4532 that I mentioned last time, and if you recall we looked at this truth table here, so that when I press my button 1, which I've wired to D0, when I press that, then these outputs Q0, 1 and 2, not interested in Q2 actually, I get 0, 0. If I press button 2, I get 0, 1. If I press button 3, I get 1, 0. If I press button 4, I get 1, 1. Perfect. And the only thing we need other than that is a clock. Now, what I found is you've got this pin E0, and if you look up at the description of E0, let's just find it. Yes, it says here, the enable out E0 is high when no priority inputs are present. So it goes low when you press a button, when you release it, it goes high. So every time you press and release a button, you effectively get a clock cycle. Okay, so we've got everything we need now. So let's just have a look at my block diagram again and see how it bolts together, okay? So this is what we had last time. We had our two binary buttons here, A and B. We had a separate button to simulate a clock, and the output from that we latched, the latched output from that we wired both to an LED, which I call A and B, and we also wired it into our multiplexer, this device up here, and the outputs from that, which fed this 6 volt through to whatever channel you selected, to one of these LEDs, okay? So now if we introduce the multiplexer, that's how I wired it. So I've got now my 4 buttons, okay, which I showed right at the beginning, the concept. That goes into the 4532 chip. I've got my Q0 and Q1 outputs, so that's the binary outputs going into my flip-flop. And that E0 pin is going into both clock inputs of the dual flip-flops on that 4013, and then the rest stays the same. So now when I press this first button here, I should get 0, 0 out of here. So and that latches on my 4013. My AB should be off, and my channel 0 should route through to 6 volts, so that illuminates. If I press this button here, my second button, then I get 0, 1. That latches. I get the A will illuminate, B won't. Then channel 1 routes through to my 6 volts, so the second LED illuminates, and so on. Okay, so we are getting there. So let's just have a look at that on the breadboard. Right, okay, so my ABs are off at the moment, so I've got a 0, 0. And my first LED there is illuminated. So that's as if I pressed this button here, and I did actually press that button before I started the video. If I press the second button, there you go, I've now got 0, 1 as my AB. It's selected the second LED. If I press the next one, I've got 1, 0, it's selected the next LED, and the next one I've got 1, 1, and it's selected the next LED. So that LED is lighting because this 6 volts is routing through the channel that's selected by the AB signal coming off of this flip-flop, and that is triggered by this encoder, and the encoder is set by whichever button I press there. All right. Now that's great, and I actually like the fact that when I press that button, I know that it's that one selected, and when I press that, I know it's that selected. So these LEDs I actually want to keep. So I'm going to use the X routing of this dual multiplexer to drive the LEDs, and so I will keep that tied to 6 volts. And then I'm going to use the Y multiplexer, that's because it's a dual multiplexer, isn't it? I'm going to use that to route my reference voltage onto the ANS input. So all we've got to do now is get my reference voltages wired onto the corresponding data pins there, or sorry, the channel pins, and then we got to build some kind of output driver with the regulator to go into the ANS. So if you recall, that's my buttons there, and we've got to get our output driver here to regulate the voltage here to whatever I've passing through, because this and this will have an influence on the voltage. So I want this to drive it and maintain it at whatever voltage I'm choosing through pressing those buttons. Okay, so let's build up the next stage. Okay, so we had all our switching circuit running already, but what we needed to complete was the voltage references. We needed 4 voltage references. We'd already done one of them. I've now completed the other 3, and they are over here. Look, that's a little resistor pack there, and I've got 1, 2, 3 Zener diodes and some resistors, and actually one of them's tied to ground. So just as a reminder, if I can get this drawing in here, this is how I've done it. There we go. Shove the meter out of the way. So we needed a low voltage fault reference of anything less than 0.3 volts. We needed a low ambient sort of simulated environment, and that's anything between 4 to 4.7 volts. We need a high ambient simulation, which is 0.4 to 1 volt, and we needed a high voltage fault condition, which is anything greater than 4.8 volts. Okay, so with low voltage, anything below 0.3 is a fault. So nice and easy, just tie that to the ground. All right, I didn't have to. I'm not going to mess around with Zener diodes and resistors. We just take it to 0 volts. The low ambient we'd already done before, so I've actually changed this resistor now, and there's a reason for that, and that is because I've upped the supply voltage to 12 volts. And there's a reason for that, which I'll come on to later. But anyway, I've got a 4K7 resistor here. That's just to limit the current going through this diode. Otherwise, you'll have loads of current going through to bring it down to somewhere near this Zener diode voltage. But we were actually getting 4.3, and we still are, even though this is at 12 volts. Okay, so it's not quite a 4.7 volt Zener diode. They're not that precise. Then my high ambient noise condition needed to be between 0.4 to 1 volt. So again, 12 volt supply, 4.7k resistor here. I plucked out a 3 volt Zener diode, and then I played around with resistor values here. I roughly knew what I needed. And then this little device here, well, that's actually a configurable resistor pack. You sort of program what resistor value you want. So it's quite good for that kind of thing. And I've worked out that if we got a 2k and a 1k voltage divider here coming off of this point, then we end up with 0.85 volts. So that's perfect, that's in that range. And for my high voltage fault condition, I needed something over 4.8 volts, 12 volt supply still, 4.7k resistor here. I haven't written the Zener diode. I think that was actually a 5 volt Zener diode, and I'm just trying to find my pen to write it in. No, I'll do that later. Yeah, that was a 5 volt Zener diode, but I'm actually getting 5.1 in this combination. All right, so let's now look back at the breadboard and let's measure it. So ignore this at the moment, this chip and this bit of wiring here, but I'm just going to take this lead off of that chip, because this here is coming off of the multiplexer chip. So it's the Y channel routing, you know, Y0, Y1, Y2 or Y3 to this common Y output, and so that's where I expect to see my selected voltage on. So let's just turn the supply voltage on. So I've got 12 volts on my programmable power supply, and I can see I'm currently draining just 13 milliamps. So all of this circuitry is only draining 13 milliamps, and that's including that LED there, which is probably 10 milliamps on itself. So that's not bad at all. I'm pleased with that. And let's just put my voltmeter on this leg here. Oops, and there. Okay, so I'm on this button here, so I've pressed this one, which is my high voltage fault condition, and you can see I'm getting 5.28 volts. All right, so that's more than the 4.8 volts to generate a fault condition. The blue button, which is the high ambient condition, where we want something between 0.4 and 1 volts, and I'm getting 0.8. So that's good. And I press my green button, which is the low ambient condition. That should be anything between 4 to 4.7. I'm getting 4.3, which I think I had before. And my low voltage fault, which can be anything below 0.3. Press that, and yeah, I'm getting 0 volts because it's tied to 0 volts. So you'd expect that. So that's good. So I'm getting the right output dependent on which selector I pick here. I've taken off this sort of binary LED for now. We're not interested in that. We know all of that binary selection through here, and the latching all works. We've already proven that. So the next stage then is getting this output stage done with some kind of regulated control. All right. And as you probably suspected, that is that little chip there, which is an op amp. So let's have a little look at that. Okay, so this chip here is an op amp, okay, and that op amp is what's going to regulate our output and be able to drive a bit more current than you can from that multiplexer. So if you've not come across an op amp before, I'm not going to go into it in great detail, but there you go, that's the symbol for an op amp there. The chip is actually a dual op amp, I'm only using one of them. That's the symbol there. This is called the non-inverting input. It's got a plus symbol, and it's called the inverting input. It's not the supply. The supply is normally shown here as well, but you can just assume it's got a supply, which it has. And what it does is an op amp will drive its output to do whatever it takes to make the inverting input match the non-inverting. So if I put a voltage here, my voltage reference on this non-inverting, it would do whatever it takes on this output to make this the same as that, okay? So I've wired the output to the base of a PNP transistor. Sorry, not a PNP, an NPN transistor. And the base will control the current from our 12 volt supply through this 10k resistor and down to ground, okay? So this effectively is kind of like a voltage divider, because this transistor is like a variable resistor, and this base is controlling how resistive this is. And you'll see I've wired here on my output another cable coming back to my non-inverting input. So what will end up happening is the output of this op amp will drive this transistor to do whatever it takes to make this output match that input, all right? So this is my voltage reference. If that was 4.3, this will be 4.3 here, regardless of what else is wired on there, to a degree. It's whatever this transistor can drive from this and this. It's got limitations, of course, but we're well within the capabilities of driving to the voltages that we need, all right? So let's have a quick look at that on the breadboard. So there's the op amp there, as I said. This leg here is the non-inverting input coming back from sort of like our sense voltage, if you like, and this is the output from the op amp, this lead here, and that's going to the base of the transistor to control it. I've got a 10k resistor there to ground, and then this is the supply voltage coming in to the collector, all right? So where I want to sense this then is on the output here, so I tap in there, all right, and I'm currently turned on, so we're on our low voltage fault, and we're getting 0 volts. We go to the next one, the green button, I've forgotten what that is, that's our low ambient, and we get our 4.3 volts on here coming through that transistor. And if I press the high ambient, we get in just below 1 volt, which is good. And if I press the high voltage fault condition, we get 5.2 volts. So that's good, that's coming through that transistor. So I can put more current through that, and it's regulated through this op amp control. Now, so let's just simulate this here. Just simulate our effective load that we have back at the rack. So we've got this 240 ohm resistor pulling it back down to ground, haven't we? So that's effectively a load on the voltage coming back from the ANS. So we need to see what impact that has on our regulated voltage. So that there is a 240 ohm resistor, which will go to ground when I plug that into ground. And I'm going to go through a switch just so as I can turn that resistor on and off within the circuit, if you like. So let's just wire that in now. It'll take me a couple of seconds. So that's my ground, and I want to wire that into my output. I've got one little leg I can squeeze in there, I think. Yep, okay, so there we go. So at the moment, got no load other than my 10k, which is virtually nothing really. Sorry, my 10k over here. That's my sort of dummy load when the system's not connected to anything, when this is not connected to anything. So now if I connect my 240 ohm to ground by pressing the switch I'm doing now, you can see it's not affected. It's still 5.2 because the op amp is regulating it. If I go to my other voltage reference, there you go, 0.8, I press the button. It fluctuates a little, but that's still well within our range. If I go to the fault condition, which is 5.2 volts at the moment, take it to ground with my 240, fluctuated over there, what's that, 1 millivolt it jumped, but it's solid now. And my low voltage fault condition, 0, press the button, that's not going to do anything anyway, because we're just pulling it back down to ground, it's already ground. So that's brilliant. So we can put virtually any load on this output, and the regulation controlled by this op amp will keep it at our reference voltage. The route, starts way over here and gets routed all through here by selecting the relevant button. So I think that's about it. That's the circuit built as far as I'm concerned. I might want to have a bit of safety, maybe a fuse on this. The back at the rack here, the supply going to an ANS normally has a 100 milliamp fuse going to it. I could do something similar on the board. I could put some current regulation on the output, say never exceed, I don't know, 500, not 500 milliamps, perhaps 50 milliamps or whatever, sort of half the load. Oh yes, and the other thing is the supply to this is going to be from the 24 volt supply from the rack. So I said to you, I've upped this to 12 volts. It's currently being driven by 12 volts on the supply rails here. But I'm going to use another voltage regulator to step that down from 24 to 12, okay? So if I'd have kept this at 5 or 6 volt supply running all this, then that voltage regulator is doing a lot of work, dropping 24 down to 5 volts. By driving this at 12 volts, you kind of reduce the current, and it gives the voltage regulator a bit of headroom, really, and it won't overheat, or it won't be so inefficient. At any rate, the next step, I would say, is to perhaps get that 24 volt regulator wired in and test it on a Vipedia, and let's simulate an ANS with some broadcasts and see what it does to the attenuation. All right, I'll catch you later.